Hey everybody, today we are going to talk about writing trigonometric proofs. This goes along with page 460 in your textbook. Up until this point, we've been simplifying trigonometric expressions. Now we're going to use our skills from that with all the identities that we've learned so far, and we're going to start to prove some more complicated identities actually exist. So how do we do that? Well, it's pretty simple. To prove or verify that an identity is in fact true, what we're going to do is simplify one side of an equation until the point that it shows that it's equal to the other side. So you're only going to manipulate one side of the equal sign at a time. You're never going to add or subtract a term from one side of the equal sign to the other side. So you're only going to look at one side at a time. We're going to use trig identities to simplify one side at a time. And there's often more than one correct method to do this. So if you're working on proving or verifying an identity and your neighbor's working on proving or verifying an identity, you might go about it in two completely different ways and still end up proving the identity. And that's all right. So here are some strategies that I like to use when I'm verifying trigonometric identities. Number one, remember, the proof begins with the expression on one side of the identity, and the proof ends with the expression on the other side. Now, in between, the work that shows that we can simplify one side until we get to what's on the other side has to consist of showing a sequence of expressions where it's easily seen that one step corresponds to the next and leads to the next. It's a good idea to always begin with the more complicated side. That's just because the side that's more complicated has more things you can do to simplify it. Don't forget, write justifications for each step along the way. I may have mentioned before, but I'm going to say it again. Don't move terms across the equal sign while you're writing proofs. We're not trying to solve an equation. We're trying to show that one side is equal to the other side. And for goodness sakes, don't skip steps. The whole point of the proof is to be able to read all your work so that you can see how very clearly and logically one side can be simplified to equal the other. And that proves that they're equivalent expressions. That's the identity part of it. So don't skip steps. So here we are with example number one. We're given this identity and we're asked to prove that it is in fact true. So let's go ahead and start with one of my very favorite strategies. I like to change everything into sines and cosines and then simplify. I'm going to pick the more complicated side. Hopefully you already noticed that this side here seems to be a little bit more complicated than negative sine squared. So that's the side that I'm going to start with. I'm going to change everything into sines and cosines, which isn't going to be too hard since we only have one thing that's not actually a sine or a cosine. Besides the number one, I guess. So I've got 1 plus the cosine times 1 minus, now instead of secant, I'm going to write 1 divided by cosine, since secant is the reciprocal of cosine. And this whole thing is getting multiplied by cosine. Now I don't need to write equals sine squared because the whole point of this is that we're trying to show that this side does equal sine squared, negative sine squared. But what I should do at this point is write down my justification. What did I do to show that, to go from this line to this line? So all I did was I applied a reciprocal identity. Very good. So now let's go to the next line. I'm going to do each line in a different color so that it will be easier for you to see like my change in the work. I hope that works for you guys. At this point, this is a lot of multiplication happening here. I'm going to go ahead and use the distributive property. So I'm going to multiply the cosine of x that's here to 1 divided by the cosine of x and also to this one right here. So I've got, haven't messed with this one yet, so that is, oops, supposed to be in a different color. Let's go with black. So I've got the quantity 1 plus the cosine of x, haven't distributed that yet, times, let's see, if I multiply the cosine of x times 1, I get the cosine of x, minus sign. And if I multiply the cosine of x times 1 divided by the cosine of x, my cosines will cancel out, leading me to 1. So my justification for this step is the distributive property. I personally feel that the distributive property is one of the most important properties in mathematics. It shows up everywhere. And check it out. Looks like we're going to have to do it again. I've got a binomial times a binomial. Let's go ahead and multiply it together, see what happens. So I've got 1 times cosine, which is cosine, 1 times negative 1, which is negative 1, cosine times cosine, which is a positive cosine squared, and cosine times negative 1, which is negative cosine. And I closed my parentheses because I started parentheses here. You don't necessarily have to have that. That was, again, the distributive property. Maybe you're having an aha moment because hopefully you see that when we have a positive cosine and a negative cosine, those can be subtracted and we'll get 1. I'm sorry, we'll get 0. Why did I say 1? Goodness me. So that justification is going to be subtraction. Now, this looks kind of interesting to me. I know that when I see a 1 and some kind of a square, that can often be a Pythagorean identity. But my Pythagorean identity usually says 1 minus cosine squared, not negative 1 plus cosine squared. So in this problem, I think what I could try and do is I could try and factor out a negative 1 and see if I can get it into the proper form for one of our Pythagorean substitutions. So I'm going to factor out a negative 1. Negative 1 times positive 1 gives me negative 1. And negative 1 times negative cosine squared gives me a positive cosine squared. So I just did, my justification is going to be factor. So I did factoring. Now it can be even more clearly seen that 1 minus cosine squared is really sine squared. That's going to be a Pythagorean identity for my justification. Very nice. Our final step is just to multiply negative 1 times sine squared, and I'll get negative sine squared. And that's just multiplication for my justification. Oh, that's in blue. Interesting. Once you've finished, and you'll know you're finished because what your simplified result is matches what's on the other side of the equal sign, you're going to end your proof. The way you end your proof is one of two ways. Either you write QED, which is Latin, stands for quod erat demonstrandum, which means that which we were trying to prove. Or you can use the tombstone, which is a little square or rectangle. Sometimes it's left white, sometimes it's colored in. It's up to you. So choose either QED or your tombstone and end your proof. I think for this one I'm going to stick with QED. And that's how you know you're done. All right, let's try another. Here we go. So I've got cosecant squared of x minus 1 divided by cosecant squared. And this is going to equal cosine squared, and we have to prove it. Well, up here in the numerator, it does seem like I might have something that's set up nicely for Pythagorean identity. So maybe instead of trying to change everything into sines and cosines at the beginning of this one, maybe I'm going to try and use a Pythagorean identity for my substitution. So I think that's what I'm going to do. Let's try it. So cosine squared minus 1 is a Pythagorean identity that represents cotangent squared. So I'm going to rewrite this side. So instead of writing cosecant squared minus 1 in the numerator, I'm going to write cotangent squared. And then I'm going to rewrite my cosecant squared down below. So my justification here is the Pythagorean identity. Okay, very nice. Well, I'm trying to show that it's going to equal cosine squared. So at some point, I'm going to have to involve cosine in this. That's no big deal. I think that my next thing I'm going to do is replace the cotangent and the cosecant and write them in terms of sines and cosines. So cotangent is really cosine divided by sine. Therefore, cotangent squared is really cosine squared divided by sine squared. And that's a reciprocal identity. But don't forget, we also are dividing by cosecant squared. And cosecant squared is the same as 1 divided by sine squared. So I'm using a combination of the reciprocal and quotient identities here. Very nice. Well, this is set up nicely. It's a complex fraction, so we could go ahead and divide. You can multiply by the reciprocal if you like. So I'm going to end up with cosine squared times sine squared. Divided by sine squared times 1. That is simply division. We could even write dividing complex fractions if you want to sound fancy. So we have a little simplifying that we can do here. Recall that any number divided by itself is 1. So I have sine squared divided by sine squared. That's a little bit more division, isn't it? And I'm left with cosine squared divided by 1, which I think that we can just leave as is, just cosine squared. So this again was division. Please, please don't write canceling, okay? Because it is in fact division. And now check it out. What we have on one side simplified until it became what we had on the other side. As a result, we have now proven that this is in fact an identity. So when you're done, make sure you end your problem with either QED or the tombstone. That was a pretty wild tombstone, but there you go. They call it the tombstone because it's the end. Okay, that was my little Halloween humor, but let's move on. Example number 3. We have cosecant squared minus 1 divided by cosecant squared, and that's going to equal cosine squared? Well, there is another way you can prove it. Remember when I said your friend might solve it a different way than you? Maybe you'll even solve it a different way from yourself. So let me show you another way you can think of solving this problem. Notice that I have 2 terms in my numerator. What I can actually do is split this up into 2 separate fractions. You get addition or subtraction in your numerator when you combine fractions that have a common denominator. And we can actually split them apart again if we wanted to. So let's split these guys apart. So cosecant squared minus 1 divided by cosecant squared actually comes from the problem. Ooh, my pen just went crazy. Cosecant squared divided by cosecant squared minus 1 divided by cosecant squared. Notice that these are in fact equivalent because when your denominators are the same, you can combine the numerators. And so that would make this fraction if we were going to subtract. But we can go backwards as well. So this is just a division rule, you could say, or you could say subtraction if you want to. All right, well, we can simplify this, can't we? I know that cosecant squared divided by cosecant squared is 1. And I also know, well, let's not combine together steps, so let's take it slow. So that was just division. Again, more division. Now, I know that 1 divided by cosecant is really sine, and so I know that 1 divided by cosecant squared is really sine squared. So I'm just going to apply that reciprocal identity rule. And hopefully you're recognizing already what we have written here, because 1 minus sine squared is another identity. It is the Pythagorean identity. So 1 minus sine squared is really cosine squared. And that is what we had on the other side of our equal sign. So I was able to simplify the left-hand side until it equaled the right-hand side. And that's how I know I proved my identity. Another way. So this time I'll write QED. And don't forget to put your Pythagorean identity as your justification. When you guys take your test, you're going to have to write your justifications too. So it's really good practice for you to do so when you're doing your homework or when we're practicing together. Okay, so let's try this problem. So we've got the sine of x divided by 1 minus the cosine of x. Well, you guys can read it. It looks pretty complicated. So on first glance, I think that the left-hand side looks a little bit trickier than the right-hand side. So again, I think I'm going to go ahead and start by simplifying the left-hand side on this problem. So since everything is already written in terms of sines and cosines, I think that I might have to try something new. Let's see. I know that I'm going to try and end up turning it into one fraction that has a sign in the denominator. So sometimes you're going to have to use what you see on the other side to kind of help inform what your choices are going to be. In this case, I think that I'm going to have to try and combine together these two fractions to turn it into one fraction with the goal of getting sign in the denominator. So I'm going to start by trying to get a common denominator, and then I'll be able to combine these two fractions together. So I don't know. I think that the easiest way to get a common denominator is to multiply these two denominators together. So I'm going to multiply the top and the bottom of this fraction by 1 minus the cosine of x. And then I'm going to multiply the top and bottom of this fraction by the sine of x. Which looks kind of sloppy, but I'm going to write it all the way out, and I hope that it will make some sense. So now I've got the sine of x times the sine of x, which is the sine squared of x, plus 1 plus the cosine of x times 1 minus the sine of x. I'm sorry, minus the cosine of x. All divided by 1 minus the cosine of x times the sine of x. So what did I do here? Man, all I did was get a common denominator. Very good. Now let's go ahead and do a little, I don't know, distributive property. So little distributive property here. I think that I'm going to keep this 1 minus cosine x here for right now. I'm hoping that somehow I'm going to get it to cancel out because I do have the sine of x alone in the denominator on the side I'm trying to turn this all into. So maybe something interesting will happen up here. Who knows? Let's check it out. So with the distributive property, I'll get 1 times 1, which is 1 squared, or just 1. I'll rewrite this bit. I've got 1 times negative cosine, which is negative cosine. I'll get cosine times positive 1, which is positive cosine. Ooh, hoo, hoo, hoo. And then I'll get cosine times negative cosine, which is a negative cosine squared. All divided by, and again, like I said, I'm not going to distribute that denominator yet because I'm really hoping that I'm going to be able to reduce this fraction and get that sine of x alone down there. That's my hope anyways. So my justification here was just I used the distributive property. Alrighty, well, let's go ahead and simplify. I know that cosine minus cosine is 0. So this is going to leave me with sine squared plus 1 minus cosine squared. Okay. Alright, so that was just a little bit of subtraction. Not too fancy. But did you see what that left us with in the numerator? I saw it. That looked to me like a little bit of the Pythagorean identity. Do you see it? There it is, 1 minus cosine squared. My handwriting got a little crazy right there, but maybe I was just excited. So 1 minus cosine squared is sine squared. So let's pop that in there. Plus sign in between them because 1 minus cosine squared is sine squared, all divided by 1 minus cosine times sine. And that is the Pythagorean identity. Okay, well, we know that sine squared plus sine squared is 2 sine squared. So let's add. And while I know I can reduce this sign with one of those two sides, that would be the wrong option here because I want to keep that sign in the denominator. Remember, sometimes you're going to have to use this side to help you with what to do next. I want to keep that sign there. I'm happy with that sign being there. So we got to keep it there. What we also have to do is write our justification. We just did addition. But now, what to do? Well, I do see sine squared, and I know that when I see a square, it usually makes me think of a Pythagorean identity. So let's try using a Pythagorean identity here. I know that sine squared is really 1 minus cosine squared. So I could replace this with sine squared being 1 minus cosine squared. And that Pythagorean identity is also quite nice because it is also a difference of two squares. So that's factorable. So I've got 2 times, let's see, 1 minus cosine squared is really 1 minus cosine times 1 plus cosine. And that was just factoring. Oh, do you see it? Do you see it? Look. Any number divided by itself is 1. So we've got 1 minus cosine divided by 1 minus cosine. That division is going to do some great things for us. That's going to leave me with 2 times the quantity 1 plus cosine x divided by the sine of x. And so let's write our justification. That was simply division. If I go all the way back up to the top, that's what I was trying to get that side to look like anyways. 2 times the quantity 1 plus the cosine of x, all divided by sine. You know what time it is. Q E D. And that's the end. You might find it beneficial to rewatch this video again after you've answered the questions, especially this last one, because some of our more challenging identities are going to be a little lengthy like this. But if you keep sticking to it and you just keep simplifying, I know that you can be excellent at this as well. I hope you enjoyed the lesson, and we'll see you next time.